Let us prove Fermat's Little Theorem. Fermat's Little Theorem states for a prime p and an integer a to the power p is congruent to a mod p. There are several methods of proving it. We will prove Fermat's Little Theorem by the principle of mathematical induction on the base a. So we will choose a equal to 1, 2, 3, 4 and so on. In other words, we will choose a equal to positive integer and prove it by mathematical induction. Observe that for a equal to 0, the result is true as 0 to the power p is of course equal to 0 for any prime p, and 0 is congruent to 0 mod p. For a equal to 1, 1 to the power p is again 1 and 1 is congruent to 1 mod p. So we can frame induction hypothesis that a to the power p is congruent to a mod p for some positive, we are not saying for every positive, for some positive integer a, for some positive integer a. So far so good. Now somehow we want to show that whenever it is true, whenever Fermat's theorem is true for a, it's also true for a plus 1. So let's expand a plus 1 to the power p by using binomial theorem. A plus 1 to the power p is p choose 0, a to the power p plus p choose 1 or pc1, a to the power p minus 1 plus p choose 2, a to the power p minus 2 plus dot 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 plus p choose k, a to the power p minus k plus dot 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 plus p choose p a to the power 0. Now p choose 0 is of course equal to 1, so this a to the power p plus p choose p is also equal to 1, so plus 1, a to the power 0 is 1 as long as a is not equal to 0. For a equal to 0 we have already shown it to be true, so we assume a not equal to 0. So comma a not equal to 0. Now a to the power p plus 1 plus p choose 1 p choose 2. Okay, let's write once more. P choose 1 a to the power p minus 1 plus p choose 2 a to the power p minus 2 plus dot 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 plus p choose k a to the power p minus k plus dot 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 plus p choose p minus 1 a to the power 1. Now what we want to say is that these all are all divisible by p. Then only we can say that since a to the power p is congruent to a, so by our induction hypothesis we can say that a plus 1 to the power p is congruent to a plus 1 mod p. So somehow we should be able to show that these are all divisible by p. So for k greater than or equal to 1, less than or equal to p minus 1, p choose k is simply equal to factorial p by factorial p minus k times factorial k, and that's equal to p times p minus 1 dot 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 p minus k plus 1 divided by factorial k. That can simply be written as factorial k times p choose k equal to p times p minus 1 dot 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 p minus k plus 1. The right hand side is definitely a multiple of p, so we can say, factorial k, we can say that factorial k times p minus k is a multiple of p. Once again, factorial k times p choose k is divisible by p, comma, is k changes from 1 to p minus 1. So far so good. We are already assuming k changing from 1 to p minus 1. Now however factorial k and p, but factorial k is relatively prime to p, relatively prime to p. Once again, factorial k is relatively prime to p. What does that mean? Factorial k and p do not have any common factor as k changes from 1 to p minus 1. So, p has to divide factorial k times p choose k, but p cannot divide factorial k, so p has to divide p choose k. So, p choose k is divisible by p. Divisible by p. That means, so this quantity p choose 1 is divisible by p, p choose 2 is divisible by p, p choose k is divisible by p, p choose p minus 1, all are divisible by p. So we can say that a plus 1 to the power p, a plus 1 to the power p is congruent to a to the power p plus 1 mod p. Now, by our induction assumption, a to the power p is congruent to a mod p. By our induction assumption, a to the power p is congruent to a mod p for some positive integer a. For some positive integer a. And so we can combine these two and say that a plus 1 to the power p is congruent to a plus 1 mod p whenever a to the power p is congruent to a mod p. Whenever a to the power p is congruent to a mod p. What does we mean? But we already know that for a equal to 1, this is true. So if I write a equal to 1, then I can say that 2 to the power p is congruent to 2 mod p. Again, if 2 to the power p is congruent to 2 mod p, by choosing a equal to 2, we find that 3 to the power p is congruent to 3 mod p. Again, by choosing a equal to 3, we find that 4 to the power p is congruent to 4 mod p. And if we continue this process, we can say that, so by principle of mathematical a to the power p is congruent to a mod p. For a equal to 1, we did it in the beginning. Then by our induction, by choosing a equal to 1, we found it to be true for a equal to 2. And again, by choosing a equal to 2, we found it true for a equal to 3. And again, by choosing a equal to 3, we found it true for a equal to 4, and so on. And we have already shown it to be true for a equal to 0. How about negative a? We are saying that it is true for every integer a. Of course, if p equal to 2, comma, this is obviously true. A square is congruent to a mod p, mod 2. Is that true? That's because a times a minus 1 is congruent to 0 mod 2. Either a has to be even or a minus 1 has to be even. If p is odd, minus a to the power p is equal to minus of a to the power p, and minus of a to the power p by our, now minus a is positive, so minus of a to the power p is congruent to minus of a, since a to the power p is simply congruent to a mod p as long as a is positive. So minus of a to the power p is congruent to minus a mod p. So we say that minus a, if p is odd, then we find that we can cancel, we can take minus 1 common. Minus of a to the power p equal to minus 1 to the power p times a to the power p, and is congruent to minus a mod p, and we cancel minus out and say that a to the power p is congruent to a mod p. So it is true even for negative a as well. So hence we conclude Fermat's theorem is true for every integer a.